Hello, my name is Amelia Doetsch, and I worked with Dr. Herring K this summer. The main focus of my project was to search for this F7 halves proton configuration in the arsenic-73 nucleus. So the way we kind of envision the structure of the nucleus is that we have these discrete orbital levels, and they each can fit two either protons or neutrons. And if we have an unpaired proton or neutron, that can determine different characteristics of the shape and the deformation of the nucleus, because an unpaired proton is more free to move between different levels. So in this research, I was focusing on the F7 halves orbital level. Now, the F7 halves orbital level has an orbital angular momentum value of 3 and an intrinsic spin value of 1/2 associated with the proton or neutron in that level. Now, in arsenic-73, we have one unpaired proton, so we're focusing on that unpaired proton. Now, the significance of this orbital level is that nuclei in this mass region cannot access this orbital level very easily. They have to have a very strong deformation in order to be able to have the unpaired proton or neutron accessing this F7 halves state. So in the mass region, there's actually only been 2 nuclei that have been observed to have F7 halves structures. This image down here shows an F7 halves band structure in arsenic-71. It forms these 2 parallel bands with interlocking transitions in between, ending at a 7 halves minus level. Now, it has been theorized that this region down here in arsenic-73 could contain an F7 halves band structure, as this level down here has been measured to have a spin in parity of 7 halves minus, and then the band structure would build up from there. So how did we go about studying this? Well, the experiment was run about a few years ago at Florida State University. A beam of carbon-14 was shot at a stationary target of nickel-62, and they fused to form selenium-76. Now, the selenium-76 is at a very excited state, so it emits some particles. What we're looking for in this experiment is that it would emit 1 proton and 2 neutrons to form arsenic-73. Now, arsenic-73 was not the only nucleus produced in this experiment. However, it was one of the more highly propagated nuclei. However, this arsenic-73 is still at a very highly excited state, so it must emit gamma rays in order to decay down to the ground state. And these gamma rays are captured and measured by the FSU detector array. And we have software that allows us to analyze these gamma emissions. So one of the main analytical techniques I used in my research was called directional correlation of oriented nuclei ratios, or DCO ratios. And DCO ratios are calculated by dividing the intensity of a gamma ray at the 35-degree and 145-degree detectors divided by the intensity of that same gamma ray at the 90-degree detector. So for the way that I did it, for an RDCO value of 0.5 would signify that the transition had a dipole radiation pattern, as seen right here, which would thus correspond to a spin change of 1. If I got a DCO ratio of 1, that would correspond to a quadrupole radiation pattern, as seen here, which corresponds to a spin change of 2. So I just want to talk a little bit about my results. This chart represents weighted averages of all of the DCO ratios that I was able to measure. Now, as you can see, these 2 values right here are highlighted in red because they ended up being very important. I was able to measure the 577 keV transition to be a dipole transition, and the 601 keV transition to be a quadrupole transition. Now that thus allowed me to measure this spin level right here to have a value of 5/2. Now if you'll recall, if we were to see an F7/2 band structure in this region, that would most certainly have to have a spin value of 7/2 rather than 5/2. So this allowed me to conclude that there is in fact no F7/2 proton occupation in the arsenic-73 nucleus. Another application of my DCO ratio measurements is that it allowed me to make certain calculations about the moment of inertia of the nucleus. So I measured moment of inertia values in this largest band so that I could infer some things about the shape and how it changes as the nucleus decays. So this graph right here shows that the moment of inertia and thus the shape is nearly constant at high spin values. However, there is a dip at a spin value of 8.5, which corresponds to a pair of neutrons splitting up. And that thus changes the shape of the nucleus. Thank you.